Great, it's recording now. Today we're going to talk about apply optimization problems, part 1. One common application of calculus is calculating the minimum or maximum value of functions, right? For example, companies often want to minimize production cost or maximize revenue or even maximize profit, right? Or if you are working in manufacturing, it is often desirable to minimize the amount of material used to package a product with certain volume, right? So in this section, I'm gonna show you techniques, I'll show you a method to maximize or to minimize a function. And we are gonna do that using derivatives, okay? Derivatives. Now, let me tell you something straight. This word optimization for us will mean two things: either maximizing or minimizing. That's it. Okay. You may say, Professor, but optimization could mean other things too, right? Yeah, I agree. But for our study here, when they say optimization, they will either mean maximizing or minimizing a quantity. That's it. Not both, either or. Okay. So this is something that we have to have very clear. Great. Now, in order to solve optimization problem, the general idea is this: they're going to give you a situation in which it will be clear that a quantity will be maximized or minimized, right? And then together with that, they're going to give you constraints, limitations for you to do this maximization or minimization, okay? So then you have to combine the goal with the constraint, and using derivative, using calculus, we will be able to maximize or to minimize the given function, right? The one that measures the quantity that is changing over time. Okay, great. So now let me explain this to you with this introduction. I have taken this nice example from our textbook, from our OER textbook, which deals with maximizing the fencing for the area of fencing for a garden. Okay, this is in your OER text. You can read there. I brought it up here. Let me use this to introduce how you should deal with this optimization problem. It says maximizing the area of a garden. A rectangular garden is to be constructed using a rock wall, which is this, as one side of the garden, and wire fencing for the other three sides. This should be the wire fencing, right? Given 100 feet of wire fencing, determine the dimensions that would create a garden of maximum area. What is the maximum area? Okay. All right. So let's answer this question. Okay. So first of all, let A represent the area. Okay. Let A be the area, right? The area to be maximized, right? Area of the garden that we're going to maximize. Now, goal, right? Goal. We have to maximize area, right? It is clear that it's a maximization problem, right? Clearly specified there. All right, maximize area of the goal. Now, this area, I can represent it with the letter A. And notice that they have chosen X to represent the width and Y to represent the length. So I think it's clear that area should be equal then to X times Y, right? X times Y. Now, this is what mathematicians call the objective function. Objective function is what you are going to maximize or minimize. In this particular case, we're going to maximize, right, our objective function area. Now, I talked to you about a constraint, right? A constraint, a limitation. And what is the constraint in this problem? Well, they say that no matter how you do this fencing, right, this rectangular fencing, you are supposed to utilize 100 feet of wire fencing, right? 100 feet of wire fencing. So wire fencing equal 100 feet, right? 100 feet. I try to remember these guys, this terminology, because on the homework, they're going to ask you, right, what's the goal, what's the constraint, the limitation, and you have to fill it up. All right, wire fencing 100 feet. Now, mathematically speaking, then x plus y has to be equal to 100, right? 100. No matter what the values of x and y are, the sum of these three quantities must be 100 feet. Simplifying, 2x plus y equal 100, right? This is the constraint. Now, notice that from the constraint, I can isolate the value of y by subtracting 2x in both sides. Y equal 100 minus twice x, right? And this value of y, I can substitute it into the objective function, right? The objective function. So this guy is gonna go right here instead of y, right? And you may say, Professor, why you're doing that? Well, notice that at this level, guys, we are doing calculus 1, right? We know how to work with functions that depend in one variable, not in two variables, right? Later on, guys, when you take calculus 2, calculus 3, they will teach you how to work with functions that depend on two variables simultaneously. But right now, I can handle only functions that look like this, right? They depend on one variable, in this case, x, for example, right? That's why you have to do the substitution there. Okay, so you get your objective function expressed in terms of just one variable, x here, right? And then after you simplify, you realize that this function is just a quadratic function, right? Quadratic function, right? So now that you have your function, try to set the limits for the value of x, right? X, the lowest it could be perhaps 0, right? If you decrease the value of x, perhaps 0, right? And the largest it could be, it's a little bit tricky to get. Look, think about it. If you have to utilize 100 for these three dimensions, right? The farthest you can go for the value of x is if x takes half of what is given here, 100, right? 50 and 50. No, yeah, 50, right? 50 and 50, right? This is with the screen case, right? Like something that would utilize everything there and will leave basically nothing for y, right? But let's consider that just kind of to look at upper bound, lower bound for x, right? Good. So this is the objective function. These are the end values, right? Endpoints. Okay, great. Now let's go ahead and maximize our area function, right? Let's maximize it. To maximize a, let's write it a of x, right? So to emphasize that this area function depends on x, right? I propose let's set a prime of x, the derivative of the area function, equal to 0, right? And solve for x, right? And solve for x, which is something that we've been doing right before. So we're gonna do it with this function. All right, so the derivative of this area function is, Deep, are you raising your hand? Do you have a question?
Yes, Professor.
Yeah, go ahead.
I want to ask you that can it be x plus y lesser than or equal to 100, or it should be is equal to?
It has to be equal. I will tell you why. Because since we are trying to maximize the area of the garden, we have to utilize everything. Yeah, because if it's less, we are not going to get to maximize it, right? We're going to get a smaller garden, perhaps, right? But since the idea is to maximize, is to utilize everything you are giving, utilizing everything. So that's why it has to be equal. Okay.
Okay. Thank you very much.
All right. Great. Yeah, guys, if you have questions, just raise your hand electronically or let me know and I will take care of it. Okay. So it has to be clear. This topic is a little bit challenging. That's why I have divided it into parts. And I will provide a lot of examples. I will give a lot of explanations. Okay. All right. So to maximize the area, let's set the derivative equal to 0 and solve for x. The derivative of this function is just, let's call it a prime.
100.
100, very good. Yeah, minus 4x, right? Excellent, right? This is the derivative of this polynomial function. Excellent. Now, we gotta set this equal to 0, right? Equal to 0 to find our critical point. Setting this equal to 0, several ways to solve this, right? Just choose one way, right? Follow one way that you feel comfortable with. I am just subtracting 100 both sides, dividing by -4 both sides, x equal 25, right? 25, great, excellent. So x equal 25 is what we call a critical point, right? But now remember, in order to find the maximum value of this function, we have this method, right? That uses a table, x here, area here, area of x, right? And we're gonna see. If x is 0, we will see what's the area. If x is 50, we will see what's the area. And if x is 25, our critical point in between, right? Let's see what the area is, right? Now, notice guys, that if you evaluate x equals 0 at your area function, which is this, right? Look, 100 times 0, 0, 2 times 0 squared 0, area will end up being 0, right? Which is really not a surprise, because if x is 0, notice in here, this will be just a line, right? Because this will be 0, 0. There is no area really, right? The area should be 0, right? Because there is no width. Similarly, for this case of 50, if you take for x everything you can take, right? 50 and 50, the 100 feet for wire fencing, there is no material for y, so there is no length. So length 0, 0 times this 0. So 50 evaluated here should be 0, right? Shouldn't be a surprise. You want to check? Well,
Professor?
Yeah,
yes.
Go ahead, Konya.
Can we check it, please?
Oh, sure. In mathematics, it's a good idea always to check, right? I said that this should be 0, right? It's not like a magician, right? Mm-hmm. It is true because what I explained, right? We're using all the material. You see 0. You see, Yvanya?
Yes.
0, very good. Yeah, always check. Yeah, always check because it's not obvious, right? It's not obvious. So but it should be 0. Don't be surprised. 0, 0. Yeah. But this is
25 is 1250.
Yeah, that would be something, right? 150. Yeah, let's check on it, all right? Yeah, if we put 25 here in this area function, what are we gonna get? Let's see. Let's check. So if we do here 100 times 25 minus 2 times 25 squared. I get something meaningful, 1,250, right? This is what we get, right? 1,250. Something meaningful, 1,250. All right. So these are the output values for our area. From here, not hard to see that the one that wins is this guy, right? This is bigger than 0, So this is the maximum area, okay? And let this serve for the following too. Notice that the evaluation at the end points, more or less, or most of the time, better said, will be kind of meaningless, right? So we will focus our attention to the evaluation that we get from our critical points, right? Those guys will be the winner 99.9% of the time, right? It will be very rare that the endpoints will win, right? Because the constructions are impossible. So sometimes we will just ignore these two and we will go straight to derivative equal to 0. That should lead us to the maximization or the minimization of the quantity we're dealing with, right? All right, great. Now that we know that this quantity has maximized the size of this garden, now I can say that since y depends on x, here is 100 minus twice x, then I can find the value of y, right? I can find the value of y. So since x is 25 feet, then y will be 100 minus twice x. 100 minus twice x. But x is this guy, right? 25. This is 50. If you take away 50 from 100, that's just 50, right? 50 feet. So these are the dimensions that will maximize the area of the garden. But not only that, now we can kind of come up with a conclusion here. Conclusion. At x equal 25 feet and y equal 50 feet, the area of this garden is maximized. The area of the garden is maximized, right? Maximized. Okay, and the maximum area can be computed. The area is, well, know how to see that if you multiply, right, these two guys, is gonna be this, right? Maximum area equal 25 times 50, right? Which is just 1,250, which we got already here, right? Evaluated the function. I'm just telling you, that this is the same as multiplying both. So it's this, right? We got it already. 1,250. In the end, attach the units is square feet, right? Square feet. Now, sometimes students, instead of writing all this out, this conclusion, students are kind of minimalist and they prefer to represent this solution, the solution to this problem, via a diagram. If you are among those students, you can do this. You can represent the garden here and say, okay, this is supposed to be 25 feet, 25 feet. This is supposed to be 50 feet. And the maximum area, the maximum of this area is just 1,250 square foot, right? So this. That can be done also using a diagram. This is the wall, right? Very good. All right, guys. So then this is an example of how you can maximize a quantity using derivatives, right? Using derivatives. Take derivatives, set it equal to 0, solve for x. That will take you to the answer most of the time at this level, right? Very good. The constraint, the endpoints, sometimes you have to check, but most of the time they will lead to meaningless solutions. So the one in the middle is the one that matters. All right, this was an example, right? I did a lot of things here. So I want you to have kind of like a guidelines that can help you to do what I just did, right? With different problems, not just with one particular problem. So for that, mathematicians came out with these guidelines. It's in your notes. Step, hints, right? Recommendations for you to follow. First, it says draw a picture and label all variables, right? In case the problem doesn't include a picture or a diagram, like in this case, right? You should draw a diagram. It will help you to visualize what you have to maximize, what you have to minimize. Number 2, determine which quantity is to be maximized or minimized. This will be explicitly shown on the problem. They will say maximize this or minimize this. So you will know, okay? It's either maximize or minimize, right? Number 3, write a formula for the quantity to be maximized or minimized. Write out in using variables, right? Your objective function, right? In this case was the area, our objective function, right? So write it out as a formula. Step 4, write an equation relating the variables that you label and use this equation to write the formula on step 3 in terms of one variable. This is the part where you use the constraint, the limitation, and then you solve for the variable y so that you can substitute it in your objective function so that your objective function will depend exclusively in one variable, right? In one variable, because that is what we can handle in calculus 1 right now, right? With one variable. Okay, and then the last step is locate maximum or minimum of the function. Step 4, using calculus. Set derivative equal to 0 and solve for the variable, right? That's what we did. All right, so let's put all this together, guys, and let's go ahead and practice some, right? And little by little, we'll show you different scenarios. First question, I want you to practice this, but first let me show you this and then show you number 1, and then I will ask you to do number 2, right? Let's start with something very, very straightforward, easy. Suppose they tell you that the velocity of a particle in feet per second is given by this formula, v equal t squared minus 2t plus 7. The formula is given, the objective function given. And not only that, notice the objective function depends on just one variable, t, right? No substitution is needed. All right, where t is the time in seconds. Question here, for which it has traveled. Find the time at which the velocity is at a minimum, okay? Minimize the velocity, right? Okay. So since we have everything that we need, right? All you gotta do is this, set your objective function's derivative equal to 0 and solve for t, okay? That's all we gotta do. So derivative of v will be equal to t minus 2, right? Equals 0. You set that equal to 0, right? And then you solve for t. 2t equal to t divided both sides by 2, t equal 1, right? 1. So at 1 second, or after 1 second, the velocity will be minimized, right? Minimized. Very good. 1, see. You follow, guys? Set derivative equal to 0, solve for the variable. I want you to kind of master that part. So can you try to do what I just did here with number 2? And let us know if you find the answer. Sometimes when I do this, some students say, Professor, you forgot the endpoints. Yeah, the endpoints you can check, right? For t equals 0, for example, 0, right? The smallest value. For t equals 0 is 7. But then notice that since this is a parabola and the parabola opens upward, right? For t equals 0 will be something, but the minimum value will occur here, right? You can check endpoint, right? But I'm telling you that the minimum will occur here at the vertex, right? Yeah. So I want you to master this. Derivative equal to 0, solve for the variable. That's what it's going to take you to the solution. I see some students.
3.
Very good, very good. Oh, yeah, very good. Excellent, excellent. Yep. You got it. Very good, very good. Yep. Deep also. Very good. Yeah. If you have the objective function, right? Go ahead and take its derivative and set it equal to 0 and solve for the variable, right? In this case, t. Okay. Let's do that. Derivative here, 2t minus 6 equals 0. Solving this linear equation, dividing by 2 both sides, t equal 3. Excellent. T equal 3. This should be the answer, right? You may say, Professor, but can you check the endpoints? Yeah, if you want to check the endpoints, you can say the minimum, the time could be probably 0, right? But for this time 0, this is going to be 5. If you put 3 there, you will see that this is going to be less than 5. 3 squared is 9. 9 minus 18 minus minus 9, minus 4. So this at time equal 3, the velocity will be negative. What does it mean? It's just coming down, right? Going down, yeah. But you can see that this guy that we're gonna get here is gonna be smaller than, this is negative 18, 9, minus 9, minus 4, right? And if you choose t to be extremely huge, infinity, this is infinity. So this is the one that is the smallest, right? Minimum. So I'm just trying to focus your attention on the critical point, right? This is the one that matters. The endpoints, they're gonna be often meaningless, as you can see here, right? Yeah. Minimum velocity. Great. Okay, guys. So now we're gonna move on. Now we're gonna see other type of problems. Okay. So let me go ahead now. Let me show you this number 3. I'm going to do number 4. Number 3 says a carpenter is building a rectangular room with fixed perimeter 100 feet. What are the dimensions of the largest room that can be built? What is its area? Okay, so in this particular problem, they are talking about a rectangular field. So they don't give you the diagram. So draw a rectangle, right, the best you can. And try to identify your rectangle dimensions with some variables, right? With some variables, x, x, y, y. You could have chosen x, x, y, y. Doesn't matter, really doesn't matter. Just have the tendency to pick for the smallest length, x. There's a reason behind that, strategically speaking, but the variables could be anything, right? I could have said A, B, B, doesn't matter. Now for the area, let's choose big A, right? Now, what is the goal here for number 3? Goal is maximize area, right? Area. Yeah, maximize area. So our objective function will be x times y. Constraint, or limitation, no matter how we design this room, the sum of x plus x and y plus y, which is 2x plus 2y, should be just equal to 100, right? 100. Objective function, constraint. From there, we have to solve this problem. But before I continue with this, I wanted to see like an animation. I want to see an animation that I have put in our website. It's available for you to play with. Let's try to, I think you got it, Goja. Yeah, excellent, right? Yeah, we're headed there because we're trying to explain, look, in our website, I have posted this applet, which allows you to change the shape of a rectangular room, keeping the perimeter fixed, right? And it gives you the area. Look, as you change the dimensions, the length and the width gives you the area. I want you to notice the following, right? When you start here and start increasing the width, the area grows, right? But there is a point when it doesn't grow anymore, decreases instead, right? Decreases, right? So where is this point where the maximum area is achieved? Well, turns out when you work with a rectangle and there is no constraints related to a wall or related to the material that you're gonna use on the walls, turns out when you are right in the middle here, 75. I can give you the link of this in case you want to play around with it. Let me put it in the chat.
Professor.
Yeah, go ahead, Deep. Yeah, here is the link.
Is it necessary to write 2x plus 2y instead of just x and y?
Yes, Deep, because notice that here there is this is part of the wall, right? But this is also part of the wall of the room. Both have to be used, right? Both, twice y, twice x, right?
But we can get the perimeter just by x into y. So
What did you say? Did you say
the area of rectangle is just x into y, right?
The area of the rectangle is x to y, but the perimeter, yes, this could be associated. Maybe I should write perimeter there, right? This is the perimeter. Yeah. The perimeter is the sum of all the length, the 4 lengths.
So it's perimeter. 2x plus y, right?
2x plus 2y.
Yeah. I mean 2 multiplied by x, y plus
x. 2 multiplied by x plus y, twice x plus y. Okay. Yes, that's correct.
Okay, got it. All right, thank you.
Okay, guys. So what I was trying to explain here is that when you are right in the middle, right? Is there where the maximum area is achieved, right? Because you continue, look, it starts decreasing, right? You are before this, it starts increasing, right? Right there, it's at 75, it achieves its maximum, right? Yeah, and what does it mean? It means that if you choose this to be the shape of a square, then you will maximize the area, okay? I'm showing you this applet, guys, because in your homework, you're gonna have an applet that you're gonna play with. The applet will help you to get the maximum area, okay? It will, but use it like I'm using here. Similarly, it's a different shape, more challenging shape, but use the applet and you will get to maximize the area, okay? But let's try to verify that this indeed a square that we have to choose to maximize our area, right? So let's see that. All right, great. So here now from the constraint, dividing by 2 both sides, right, of this constraint, we get what? We get that x plus y equal 50, right? And moreover, subtracting x in both sides, I get that y equal 50 minus x. This 50 minus x, I can substitute it into my objective function, into here, right? For y. Right there, so that I can get a function that will depend exclusively in one variable, x. So my function is going to be just like before, 50x minus x squared. Some quadratic function. Now set derivative equal to 0, solve for x, right? Solve for x. Taking the derivative, that will be 50 here, minus 2x, derivative equals 0, right? Solving this little equation for x equal 2 into 50, 25, right? 25. And that is going to be the length that will maximize the area. Now, notice that when x is 25, then y, since it depends on x, is 50 minus x, will be 50 minus 25, y will be 25, right? 25. And the area, of course, the area will be just 25 times 25, right? Which is 625, right? In the end, you may attach the units. This is square feet, this is feet, this is feet. Right? So therefore, answer very good, right? This guy. Can you try number 4, right? And it confirms, right, that it has to have the shape of a square, right, to maximize the area, right? 25, 25. Length and width are the same. Try to number 4, and then we will move on with other more complicated, more challenging, better said, exercises. Yeah, do this one. Yeah, as a hint, I will show this. Great. I see students posting answers. I choose to label the smallest distance or dimension with x. It's just me, but you can use any variable. Goya, Excellent, excellent, very good, right? Yeah. Yeah, look for the shape of a square, right? We know, very good, very excellent. So, but let's say you forget that fact when there are no restrictions, no limitation, right? That's how the final answer comes to be. But let's say you forgot that, well, then it's not a problem because the goal here, again, is to maximize area. Well, what is that area? Area x times y, right? Constraint, twice x plus twice y, the perimeter is fixed. It has to be equal to 168, right? 68 centimeters this time. Yeah, deep, very good, very good. Yeah, deep, but that's just in the case, in case nothing, there are no restrictions here, right? Because remember when we did the problem with the garden, it was not a square, the result, right? The result was some rectangular shape because there was a wall, right? But this is a very easy case where there are no restrictions. That's why we end up with a square. Okay, dividing by 2 both sides, we get that x. Here x plus y equal 81, which means that y is equal to 81 minus x, right? Subtracting x in both sides. And that I can substitute it in here, right? Into my objective function. So I'm gonna get that area is equal to x times 81 minus x. So the area is going to be this quadratic function, 81 times x minus x squared. Next step, set derivative equal to 0, solve for x, right? Setting the derivative equal to 0, I get 81 minus twice x equal 0, right? This is actually 84, be careful there. Yep. So then 2x equal 84. X 2 into 84, 42, right? 42. Then y depends on x this way, 84 minus 42. This difference is 42. So you end up with x being equal to 42 centimeters, y 42 centimeters, and the area will be 42 times 42, right? Multiply these two. And that is, they don't want the area here, they just want the dimensions, right? But in case they want the area, this should be the area. 42 times 42, 1,764. 1,764 square centimeters, right? In case they ask. Yeah, but this is enough to identify our answer is this. Excellent. Very good, guys. So now let's move on. This is another problem, but I want to save it for the end because it deals with the case when we don't have endpoints. Okay, it's a special problem, but let's hold it. Instead, let's focus our attention. Yeah, there are a couple of problems here. Yeah, probably I will do one and let you do the other. But let's pay attention to this other problem. I think it's the cube problem. Deals with the construction of a cube. Yeah, let me show you this. There are two problems here, 8 and 9. Sorry, 7 and 8. Yeah, I'm gonna do 8 because this deals with decimals, so it's more general than 7, but 7 should be similar, so you can try that. So let's try number 8. This problem is also in your homework set of problems, so let's do it together. It says, from a thin piece of cardboard, 10 inches by 10 inches, square corners are cut out so that the sides can be folded up to make a box. What dimensions will yield a box of maximum volume? What is the maximum volume? Round to the nearest tenth if necessary. Okay. All right. So following the guidelines, the guideline says draw a diagram, right? A diagram should help you to understand what's going on here. So let's draw a diagram. They're talking about a square cardboard, right? Where they have cut off, or cut out, there's a cutout, right? Squares on each corner, right? This way. Such that when you remove these squares and you fold up the flaps, right? That are left here and here, right? If you kind of fold this up, and the same here, the same here, no hard to see that what you're gonna get is a box, right? A box. Yeah, so folding this up, you will get a box, right? Yeah, so something like that. All right, so now the idea is to maximize the volume of this box, maximize the volume of this box. The question is, right, how much you have to cut such that when you fold it, whatever is left, you will get this box with a maximum volume. Since we don't know how much we're gonna cut, let's represent with X the side length of each small square here, right? X, 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 X. And let's see how we can maximize the volume of this box. Okay, now they say that the distance from here to here is 10, right? 10 inches. The distance from here to here is also 10. Now, question for you guys. When I remove these 4 squares, cut this out, and I folded the flaps, right? I get a box. What should be this height? Anybody could tell me in terms of X? What do you think should be the height? What was that, Konja?
5.
No, not necessarily, because that would be if you fold it right in the middle. But in general, like, look, if you cut this off and you fold this flap, right? Up, 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 wouldn't this just be X, right? Does it make sense, guys?
Oh, okay.
Right? Because you're folding
Yeah.
up, right? You know, yeah, X, right? Now, anyone could tell me what would be this side and this side in terms of X?
10 minus 2x.
You made my day. 10, the whole thing, since you are cutting off this and this is 10 minus twice X, right? 10 minus twice X. Excellent. And this width?
Same thing.
Same thing, right? Because we're dealing with the square cardboard, right? 10 minus twice X. Excellent, excellent. So I have the 3 main dimensions of the box, right? Now, the volume of the box, which is going to be our objective function here, is going to be equal to this in general, right? Width times length times height, right? Times height. So what is that? Well, following this, the width, 10 minus twice X, length, 10 minus twice X, and the height, we just all agree that it's just X, right? X. So now I can multiply this two binomials and this monomial and get my volume function, right? So let's do that. So I'm going to FOIL these 2 out. 10 times 10, 100, right? 100, yeah. Then I have here minus 20x. Yeah, there's more stuff there coming. So here I have minus 20x again, positive 4x squared, right? Times x. Simplify. This will be 100 minus 40x, right? These two together, plus 4x squared times x. Multiplying by x over, we're going to get 4x cubed minus 40x squared plus 100x, right? You follow, guys? Yeah, very good, very good. So now now we need to maximize this volume function, right? Maximize this volume function. So for that, I'm going to set my objective function volume derivative, right? Equal to 0, right? Equal to 0 and solve for x, okay? So if I do that, the derivative of this function that I have written here nicely will be 3 coming down multiplying 4, 12x squared, right? Minus 2 times 40, 80 x, excellent, and then this one
plus 100
plus 100, excellent, and that has to be equal to 0, right? To 0. Now, this is a quadratic equation, right? That in general can be solved using the quadratic formula, right? And this is my recommendation, guys. Sometimes you will be able to factor, but sometimes you will not. So if you want to go just straight for sure to solve this equation, since we have scientific calculators that we can use the quadratic function. So using quadratic formula, we will get this, right? We will get, and the quadratic formula requires A, B, and C, right? A will be 12, B will be minus 80, and C will be 100, right? Using the quadratic formula with A equal 12, B equal negative 80, C equal 100, we are going to get the following, right? The quadratic formula says that x equal minus B plus minus square root of B squared minus 4AC all over twice A, right? This is the quadratic formula. But now we're going to compute this using our Desmos scientific calculator, right? Yeah, let's do it. So bring it up. So we're going to use fraction form. There we will write minus B, minus 80, right? Okay, great. Let's do the plus first. Plus a square root of B squared minus 80 squared minus 4AC. A is 12. C is 100, right? All that divided by twice A is 12 times just twice A, right? Nothing else. So what is this? I got my first solution 5, right? Someone is commenting something. Yeah, very good, Deep. Yeah, Deep, we're here there. Yeah, but this is one possible solution, right? Let's don't get excited because there is another one here, right? And we have to analyze both, you will see. The other one, I copy and paste it here. I'm gonna just change the sign here, for a plus for a minus, right? Because it's plus minus. So 5 is one solution, but also 1.666, which can be rounded to 1.67, right? Is another possible solution, right? There are two candidates here. All right. So we're not sure which one should be the winner, the best, right? For the maximization of the volume of this box. So let's test them both, okay? Let's test them out. 5 and 1.66, right? Which is rounded to 1.67. So out of this, I get 5 or x equal 1.67 rounded to 2 decimal places, right? But now we go to our table, right? X here. I'm going to ignore x equals 0 because remember, for x equals 0, volume 0, nonsense, right? I'm going to start with 5 and see what I get, okay? And here the volume, right? Volume. V of x, which is this 4x cubed minus 40x squared plus 100x, right? We got this guy, right? It's up here. From here, copy here. All right, so if you evaluate 5 and this other guy 1.67, let's see what happens. Evaluating 5, you will see that something surprising is going to happen. You will see. Let's evaluate the 5 first. 4 times 5 cube, right? Cube minus 40 times 5 squared plus 100 times 5, 0. What, Professor, what? 0, is that a typo? Well, not really, guys, not really. I will explain why it's 0. Notice, if you take too much for x, right, you are allowed to take 10 here, right, 10 inches here, right? But let's say you take 5 here, 5 here, you don't leave material for the box to be constructed, right? You took too much, you took everything. That's why, since the base is not going to have an area, therefore there is no volume, right? Volume 0. Or as you see, when you replace this on the volume, it will tell you it's 0, right? 0. So for this guy, 0. But what about the other guy, right? The other guy, copy and paste here. There's another guy there waiting, another candidate, 1.67, right? 1.67. 1.67 here. 1.67 here. It gives me a meaningful volume, right? 74.07, right? Better. So as you can see, depending on X, you might have to compare them via evaluations, right? You can get something that is meaningful or something that doesn't make sense, right? So we're going to write the two results here that we got. 0 here, nonsense, right? The box doesn't have any volume, but this guy give us a good volume, right? 74.07. In the end, you may attach the units cubic inches, right? This is the maximum volume, right? Maximum volume. Okay, guys, right? Yeah. So then they want you to express the 3 dimensions, right? And the volume that we have here, right? So for that, you go back to the box. A quick way to do that should be, well, you say, okay, this guy, this is a different color, right? It's just 1.67, right? When you choose to cut that amount, the volume will get maximized. And this guy will be what? 10 minus twice 1.67, right? 1.67. Give me 6.66, 6.7 perhaps, right? 6.7, let's round it, 6.7 feet, right? And this guy the same, because the base was a square, right? Feet. So we are talking about these 3 dimensions that I will show you now. 0.67 here. 1.67 feet. The height was 6.7 feet. The width 6.67 feet. The length, right? So you gotta look for that, and the volume is 74.07. So this one looks good, right? 6.7, 6.7, 1.7 rounding to 1 decimal place, and then 74.1 rounding to 1 decimal place, right? So this should be this one. You follow, guys? Yeah, this is a classic problem when it comes to optimization. When it comes to maximize the volume of a box, for example, you will have a homework question related to this, right? In order to solve it, if you need help, look at this part of the video, or also I have attached a video there that can help you out with this, right? It's a little bit long, but I think you should be okay there. All right. So now let me show you other forms that we're gonna need for this part for optimization problems. This is a nice one. Deals with the construction of a barn. There are 2 problems that are similar here. I'm gonna do the first one, right? I'm gonna let the second one for you to do on your own, okay? Let me show you this first. It says, a farmer decides to make 3 identical pens, with 88 feet of fence. The pens will be next to each other, sharing a fence, and will be up against a barn. The barn side needs no fence, right? This part needs no fence. All right, what dimensions for the total enclosure rectangle, including all pens? will make the area as large as possible. As large as possible clearly tell us that this is a maximization problem, right? Maximization problem. All right, very good. So then the goal, let's right here somewhere, goal, maximize area, right? Yeah, the goal has to be clear. Great. So we are going to let, as usual, A to represent our area. Okay, area. But now, if you label this dimension with X, this has to be also X, X, and X, and this one with Y, right? And you may say, Professor, why you are choosing X to be the vertical one? I just choose X to be the smallest dimension, no matter what the diagram is. That's just me, right? But you can put Y here, Y, and X here. It will not matter. Okay, but now they are saying that the area has to be maximized. So the area is equal to X times Y, right, from our diagram, right? But now there is a constraint. There is a constraint, right? There is a limitation. They say that no matter how you construct this barn, right, how you fence it, the sum of X, 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 and X, which is 4X plus Y, has to be equal to 88 feet of fence, right? 88. You have to use up all this material. Now, you may say, Professor, you forgot this part. Well, it's not that I forgot. They are saying that the barn is going to be used as a wall, right? So we don't need fencing here. You follow, guys? No fencing here, just here. Once, just Y. Okay? So now, as usual, from the constraint, solving for Y, I can get that Y is 88 minus 4 times X, right? Solving for Y. And this I can replace into my objective function right there, right? And as a result, I'm going to get the following. I'm going to get that my area should be equal to X times Y, but Y is 88 minus 4X, right? So I get the area in terms of only one variable X, right? One variable X. Great, right? It's a quadratic function again. So next we set our derivative equal to 0 and solve for X, right? This is the common method, the common procedure for us to maximize or minimize a function, right? Derivative equal to 0, solve for the variable. All right, derivative of A then is equal to 88 minus 2 coming down, multiplying for 8x, right? And that should be equal to 0, right? From there, guys, you do what you have to do, right? Follow a method that you feel comfortable with. I'm isolating X by subtracting 88 on both sides, dividing by negative A both sides. We are going to get, of course, X equal 11, right? 11. Great. Now, X equal 11 will lead to Y equal, well, Y depends on X this way. So 88 minus 4 times 11. 4 times 11 is 44, right? 44 taking away from 88 is just 44. In the end, feel free to attach the units, feet here, right? So this just means that the dimensions should be given by this rectangle, 11 feet by 44 feet, right? And then look for this among the choices. 11 feet by 44 feet is here, right? This should be it, right? In this case, they didn't want you to find the maximum area, right? They just asked you to maximize somehow this, right? And we did, right? We maximized area. But they just wanted a dimension, so that's it. Very good, very good. And then you may say, right, Professor, but could you analyze what happens at the endpoints? Yes, I could. For example, right, what if x would be 0? But if x is 0, notice there is no area. There is no area, right? Area will be 0, so it's meaningless, right? And similarly, if you take too much for y, right? If you take for y 88, then x will be 0. So no enclosing, right? 0 area. So 0, 0. So don't worry, this will lead to the answer, right? Yeah. Any questions? Any comments?
Yes. Could you please explain how you got x 4x? I missed that part. Sorry.
For x, this part?
Yes.
This part? Oh, sure. Yeah, Gonya, they say that you have to construct this by placing fencing here, 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 and here, right? Not here, because the barn will serve as a wall, right? As a wall. So basically I did, right? The material of fencing that I'm going to use here is x plus x 2x plus x 3x plus x 4x. That's why I'm considering 4x, right?
Why it's not 5x? We can't do.
Oh, because it's just one fencing here, 1, 2, 3, and 5. No, sorry. 1, 2, 3, and 4, right? Just 4. Yeah. No 5. Okay. Yeah. Yeah, this y is the other part of the fencing, the horizontal fencing. That's the y. Yeah, right. Just 4. Yeah, it's tricky, right? But it's just 4 times. All right, guys. Very good. Very good. Yeah. Yeah. Be careful in the homework. I think they give you the construction of a zookeeper is constructing something. Also check the conditions, right? So maybe more than 4x or less. All right, but now try to do this on your own. Can you try this one? Is it similar? And then we're gonna move on. Okay, so let's do this. Try to maximize this. I will give you the hints. Call this x, x. This will help you. And this y. Yeah, and I hope everybody has noticed that the goal here is to maximize, right? Maximize also. Why you say that, Professor? Because it's as large as possible. This is translated as maximize, right? Goal, maximize area. Very good, very good. And last hint, use area A, X, Y, right? You use this. And then the constraint, yeah, we just discussed. The goal is just to maximize this area here, right? Yeah, very good, very good. Yeah, and if you figure out the answer, yes, let us know. I see movement in the chat room. Let me check it. Yeah, Deep, you are close, but there's something, you're missing something there. Yeah, it's very close, your answer. One of the dimensions is good, yeah. But remember, a square is when there are no constraints, right? If they would say use the 4 sides, perhaps, right? But they say the barn is one of the sides that they have imposed a lot of conditions. This is not gonna, the result, I can tell you, it's not gonna be a square. Yeah, but fix it. Yeah, you got it right. Yeah. Yeah, you got one right.
Is it B?
Excellent, excellent. B. Yes. Excellent. Right? Excellent. Yeah.
Oh, so
you gotta follow
we have to multiply by 4.
Something like that, yes. Yeah, very good, guys, that you are catching that, right? There is something related to the proportions, right? Remember, when there are no constraints at all, the rectangle achieves its maximum area when it is a square. But this one is a different problem, but there must be some kind of proportion surrounding them, right? Yeah, so we will find out. But in order to play safe, just solve the problem following the guidelines, right? You follow the diagram, area objective function is this. Then we have a constraint. Constraint should be what? Let's see. Yeah, by the way, anybody could tell us the constraint. The constraint, what's the constraint? Because they're gonna ask you for these questions on your phone. What's the constraint? For example, anybody could say what's the constraint in the chat? Or, yeah, Deep, now better. Yeah. Yeah. The limitation, the constraint should be that the amount of material, which is 1, 2, 3, 4, right? 4x plus y equal, all right? You have to use up all these 136 feet of fencing. From the constraint, you can isolate y. Y equal 136 minus 4x, right? Eliminating this. And then this can be substituted in here, right? In here. Why you're doing that, Professor? Why substituting that in there? Because I need my function to be written in terms of one variable, not in terms of two variables. And you may say, Professor, is there a time when I will work with two variables at the same time? Yes, when you take Calculus 3, they will teach you partial derivatives. When you use partial derivatives, you can work with the two variables at the same time. It's more sophisticated, but we're not there yet. For now, we have to substitute this guy in here and get our regular one variable functions that we work with in Calculus 1, right? Yeah, great. 36x minus 4 times x squared. I get a quadratic function, right? It's a parabola, right? So, and I know it's open downward, so it makes sense to say that the maximum will be achieved at the critical point, right? Great, so let's set our derivative equal to 0, set a prime equal to 0, solve for x. This is our method, right? Yeah. Derivative of this function is 136 minus 2 coming down, multiplying for 8x equals 0, right? Solve these guys any way you want. For the sake of variety, this time I'm going to transpose this over here, ax, changing its sign, right? And then just divide by 8 both sides. So x will be 136 over 8. Okay. X equal 1, 17.
7.
Yep,
17.
Great. Excellent, right? And in the end, you can attach the units, feet, right? Feet. This will maximize the area of this. But now this x has a partner, right? Has a partner, y, right? To complete the dimensions. I have the width, but I need the length now. But y depends on x, 136 minus 4x. But x, we just said, is 17. Take your decimal scientific calculator or the scientific calculator of your choice, do this computation. And then you will get 68, right? 68 feet. So I'm talking about a rectangular shape of 17 feet by, it's another way to express these dimensions, 68 feet. Very common when answers are presented. So, 17 feet by 68 feet. There you go. Excellent, right? Very good, guys. Yeah, I'm glad that you have mastered this barn problem. Now let's talk about other forms, okay? Let's talk about this financial application. I am going to show you number 11, and then I'm going to ask you to do number 12, okay? Number 12. All right, and then we will go back to those problems that I talked to you at the beginning. On number 11, it says, find the number of units that must be produced and sold in order to yield the maximum profit. The maximum profit given the following equations for the revenue and cost. Okay, revenue, R of X, 50x minus 0.5x squared, cost function, 4x plus 3. Maybe I should rewrite it so everybody can see them clearly. The revenue function measures how much money you get out of selling your items, okay? Out of selling. And the cost function measures how much you spend to produce your items that you sold, right? That you sold. But one thing is always true, guys. The difference between the revenue and the cost should be the profit, okay? So I'm gonna write it here for you to see this. Profit is equal to revenue minus cost. That's the definition of profit, right? What is left after you remove what you spent on producing the items, right? That's called the profit. And if it's positive, it's even better, right? Yeah. All right, so this profit function, I'm gonna call it, we're gonna use this big P, right, for the profit function. A big P, capital P. Revenue function is R of X, right? And cost function is C of X. These two are given, so let's compute our profit function. Profit function will be revenue function 50x minus 0.5x squared minus cost function. Allow me to write this cost function within parentheses, right? So I make sure I'm subtracting 4x plus 3, not only this 4x, right? So use parentheses there. Do the math first, simplify, right? So be 50x minus 0.5x squared minus 4x plus 3, right? Once you distribute your negative sign over. Combine like terms, right? Write this nicely. What is 50x minus 4x? Well, that's just 46x, right? Plus 3. I got my profit function. It's a quadratic function. It's a parabola that opens downward, right? Like this, right? So it's very, very natural to identify our critical point with the maximum value, right? There you go. The endpoints will not matter here. This is the maximum. All right, so now let's find it, right? Let's find it. In order to do that, remember we have our general method. Set your objective function's derivative equal to 0, solve for x. This will take you to the maximization of this profit. So derivative is what? 2 multiplying this guy. 2 multiplying this guy is just minus 1, right? 0.5 times 2 is minus 1. So minus 1x. When the leading coefficient is 1, mathematicians don't write it. So it's just this. Plus 46 equal 0, right? Derivative of your profit function equal minus x plus 46. Set it equal to 0. Solve for x. Minus x will be equal to minus 46 after canceling these two guys. And divided by minus 1 both sides, you get that x equal 46, right? That should be the number of units you must produce, sell, in order to maximize your profit, right? You follow, guys? This is this guy. 46 units here. All right. Now,
Professor,
yeah, go ahead. Go ahead.
If this is the maximum point of the parabola, that means it's the critical point, right?
If it's the maximum point of the parabola, repeat, what do you say next?
Then it can be critical point, right?
Yeah, the critical point will be the maximum point, right? Because it's a parabola. The rest of the points are below, right? All the rest of the points are below. So this will be the maximum.
So we can find this out by using the pre-calculus method that we used to do, right?
Yeah, very, very good that you mentioned it. In pre-calculus, it is shown a method using x equal minus b over 2a, it will lead you to, it will give you this answer, right? But notice that sometimes we get quadratic functions, but sometimes we get cubic functions, like the one that we got in the box. Remember, the volume of the box is a cubic function, right? So sometimes you could use methods from precalculus, but in general, you will have to take the derivative and set it equal to 0. That will be always the method that will work, right? Yeah, very good.
Thank you. Thank you.
Nice catch. Yeah, great. Now, guys, can you try number 12 on your own? I'm going to leave this here so you can use this as a guidance, perhaps. Try number 2 on your own. It's very similar. Do it. Yeah, as a hint, profit equal revenue minus cost, right? Let's start with that. Represent this with big P. This is this, yeah, continue there. Mm-hmm. I see some activity in the chat room. Well, yeah, close, but you have to fix it. I think it's close, but it's different. The answer I have here. Yeah. Yeah, check your derivatives, check everything there. Yeah.
Oh, C? Is it C then?
Yeah,
Maybe
yeah,
my sign
now.
was, oh, my sign. Okay.
Yeah.
Sorry.
Yeah, guys, always check, double check. Yeah, it's not a bad idea in mathematics to double check your answer once you finish, because often sometimes some little things are loose there. Yeah, Miguel, excellent, Miguel. Yeah, I think you got it the first try. Great. Yeah, very good. Yeah, excellent. Yeah, very good, guys, very good. All right, so let's see. Okay, so it says, find the number of units that must be produced and sold in order to yield a maximum profit. Given the following equations for revenue and cost. Revenue 5x, cost 0.001x squared plus 1.3x plus 30. I hope everybody has cleared the goal. The goal here is to maximize profit, right? Yeah. I'm telling you guys this because in the homework, they will ask you, what is the goal? Maximize profit. It comes in the body of the word problem, right? Or this optimization problem. It will say clearly maximize or minimize because it's either or, never both. Okay, so now the profit we said is revenue minus cost. So big P profit should be revenue, which is in this case 5x minus cost. Cost is this trinomial, look, 0.001x squared plus 1.3x plus 30, okay? write it within parentheses, the cost. So to make sure that you are subtracting this whole trinomial, not just the first term. Okay. Now, profit function should be 5x minus, let's distribute our negative sign over, right? Square minus 1.3x minus 30, right? Yeah, so now let's combine like term. This is the term having the highest power. So let's write it first, right? Then these two guys can be combined, right? 5x minus 1.3x is just 3.7x, right? Minus 30, right? Whenever you're not sure, right? This is no doing mental mathematics, nothing wrong against that. But if you're not sure, you want to play safe, just put it in your calculator instead, right? 3.7. Very good. So now we have our profit function. It's a quadratic function. And again, as Deep mentioned, right, if you want to follow methods that you learn in pre-calculus, how to maximize or how to find a vertex or a parabola, you can do that. But here, since we're doing calculus, when I use our general method, set derivative of our ejective function equal to 0 and solve for x. This should take us to the solution because notice this is a parabola since the leading coefficient is negative. It's a parabola opening downward, right? So clearly the critical point will lead to the maximum, right? So clearly, don't worry about the endpoints. Great. Now, derivative of this will be, let's do it here. The derivative of P is going to be 2 coming down, multiplying this guy is minus 0.002x plus 3.7. Derivative is 0, right? That's the derivative of the profit function. That should be set equal to 0. Let's solve it. So minus 0.002x equal minus 3.7, right? Dividing both sides by this guy, we should get our answer. 0.2 x equal, let's find out. Here's our calculator. Notice that this cannot be done using mental mathematics, right? So you use calculator, 0.002. 1,850. 1,850. And this corresponds to choice C, right? Yeah, 1,850 units. Yes. Excellent, guys. Okay, guys, now let's go back to those two problems that I mentioned at the beginning, right? Which are a little bit tricky, challenging, but I will show you step by step how you should go over them. And I'm gonna do one problem first, and then I will give you another one which is similar for you to do, okay? So this is to complete our form. Yeah, this is, I think, this two. Yeah, the cube we did, yeah, this. 5 and 6. I'm gonna do 5, okay? And then I'm gonna ask you to do 6. It says the following. A rectangular field is to be enclosed on 4 sides with a fence. Fencing costs $2 per foot for 2 opposite sides and $6 per foot for the other 2 sides. Find the dimensions of the field of area 670 square feet. That would be the cheapest to enclose. All right, solution. First of all, guys, let me ask you this question. What is the goal here? Goal. Anyone could tell us? Goal, in your opinion, which one?
Cost should be the cheapest.
Cost should be the cheapest, right? So we're talking about minimizing the cost, right? Very good, very good. Cost should be the cheapest. It's written there, right? So minimize the cost. That's the goal, right? So let's write it up. Goal, minimize the cost. minimize the cost. Great. Now, therefore, let's use a variable to represent the cost, right? Let's C represent cost, okay? Now, let me draw a diagram, right, to represent this rectangular field. There's a rectangular field that you have to construct, right? Let me draw a diagram, right? So the diagram could be any rectangle, right? So, yeah, but the thing is, right, we are trying to minimize the cost of fencing here, right? Fencing costs $2 per foot for two opposite sides. $2 per foot for two opposite sides, could be this and this, or this and this, and $6 per foot for the other two sides, right? Now, guys, question, critical thinking question. If I am trying to minimize the cost, right, as Deep clearly stated,
We'll use $2.
the large, yeah. So where do you think I should spend the material that costs $2? Here, here, or here and here?
Larger side.
Right and left.
Yeah, largest one, right? Yeah, very good. Because
Largest.
the idea is like this is cheap material, right? Cheap.
Oh, yeah.
Cheap. So the cheap material I should spend on the largest part of the rectangular field, right? So here I should use the $2 per foot, right? $2 per foot. This is a tricky problem. Here, right? Here and here. And for the other for the I'm assuming here this will be the shortest length, right? I should try to use this expensive material, right? Yeah, it's expensive, right? Yeah. In any case, the mathematics will tell you, right? But I'm just trying to be kind of to follow common sense, right? $6 per foot should be utilized here and here, right? Yeah. Okay, so now let's do the labeling, right? For the labeling, again, choose this to be X, X, Y, Y, or vice versa. I am going to choose X for the smallest and Y for the largest. That's what I usually do. Okay, but feel free to use any two letters of the alphabet in any order. Okay, great. Now let's write out our objective function cost, right? What is the cost? Well, if I'm going to use here this material at $2 per foot, if I'm using Y feet, the cost should be twice Y, right? Twice Y. But also I'm using that here, twice Y. So 2Y plus 2Y, which in total will be 4Y, right? Plus over here and over here. I'm using X feet here is $6 per foot. So the cost to cover all this part will be 6X, but again, 6X here, right? So this would be the cost function, right? 4Y plus 12X, right? You follow, guys? That's the cost function, right? The objective function. Now, anyone could tell me what is the constraint? Constraint.
Delete that. It's going to, yes.
The area, well, what do you say? The area should be this, right?
I don't want page numbers on my signature.
Equals to
Signature pages.
Yeah.
I wanted to.
Great, great, great. So the area should be this, right? Yeah, this is the constraint. Very good, guys. Look, this area, this is the constraint. They want, no matter what you do, how you design this, the area should be equal to this. XY should be equal to 670. I know that in previous problems, the constraint was the perimeter, right? That there was some fixed perimeter to use. But in this case, the area is the constraint because they want the area to be fixed, to be 670, no matter what you do. Okay, so this is the constraint. So now from the constraint, dividing both sides of the constraint by y by x, better set, because we want to isolate y, right? We will get to isolate y. Y is going to be equal to what? 670 over x, right? Isn't it? Yeah. Now, this y that we got here in terms of x, we're going to place it here into our objective function. Professor, why you do that? Well, again, guys, because I'm working in calculus 1, I can deal with functions in one variable, not in two variables. I don't have partial derivatives yet available, right? So we got to do this. So cos then can be expressed as follows: 4 times y, but y is this guy, 670 over x, right? Plus 12x. Great, right? Now let's clear this up. What is 4 times 670? Well, let's find out. 4 times 670 is 2,680. 2,680 over x plus 12x. Okay, that's this. Now, since I'm going to take derivatives, allow me to rewrite this as follows: 2680x raised to minus 1 plus 12x. Okay. That way I can take easily the derivative, right? Using the power rule. So now set c prime equal to 0, solve for x, right? This promises to give us the answer, right? So the derivative of this function is going to be the following. Let's do it here. Negative 1 comes down, multiplies this guy, minus 2680. X raised to minus 1, that is a minus 2, right? Minus 2. Derivative of this part, 12. That equals 0. I'm going to transpose this to this side. I will get 12 equal to 680 to minus 2. Now, this is this. Once I write x raised to minus 2 as x squared on the denominator here, right? Bring it down to make the exponent positive. Multiply both sides by x squared. Right? Isolate x, right? So cancel here. I'm going to get then 12x squared equal to 680, right? Divide by 12 both sides of this equation. You get this. Take square roots. You get this finally, right? Now this can be computed in our calculator. So let's do that. So square root fraction form 2680 divided by 12. 14.94, right? Rounded to 2 decimal places. That should be enough, 2 decimal places, other rounding. So 14.94. 14.94. And in the end, you may attach the units. You're dealing with feet, so feet here, right? Very good. Now, this is x, right? This is x, but I think they want both x and y, right? Yeah, x and y. So let's see.
Please scroll down a little bit, sorry.
Yeah, sure. Yeah, is that okay? The height? Yeah.
Yes. Thank you.
Yeah, great. Yeah. Okay, great. So now that we have x, we can find y, right? We can find y. Okay. So then we can say, right, then y can be gotten from here. Look, y is 670 over x, 14.94, right? Can calculate this too. Let's do that. 670 over 14.94. Aha, 44.85, right? 44.85 rounding to 2 decimal places. 44.485. 44.85 and then feet, right? Feet. And so you can see, right? This should be X, right? At $6, 44.8, right? And 14.9 feet at $2. So this, let's use a different color. This was X was 14.94. And this Y ended up being 44.85. Yeah, $2. Yeah, so which choice do you pick? Could you tell us?
It's B, no?
Try, Gonja, try. Look carefully. Any other opinion? Look at the pricing. Look, this is saying. Now, Gonja, you may make it.
Okay.
Yeah, great. It's tricky, guys. That's why I save this for the end, right? For the end, because it's very tricky. Look, anyone will go for this very easily, but look at the pricing. And that's why we did this reasoning at the beginning, right? Also to be consistent. Look, I ended up with the smallest dimension here and the largest here, right? Everything looks nice. When you choose pair up well, 14.94 is at $6. So it's this, right? And 44.85 feet, right? Is at $2 per foot. $2, right? So this guy. Tricky problem, guys. All right, can we try this one then? Can you try this on your own? Number 6 to finish. Try. Give it a shot. Yeah, follow what I did, right? That's I'm gonna give you the hint now. This is the cheapest. This is the expensive one, right? Expensive. The cheap. Even if you don't consider that, the mathematics will tell you the answer, but it's better to do it nicely like that. Yeah, use a couple of colors for the rectangle. Yeah, the cheap one here. And the expensive here, right? Yeah, because you are trying to minimize the cost. Yeah, and I call the smallest X. The largest Y is me. If you follow me, you can try this, but so the way you set the variable, that shouldn't matter in the end. And this is gonna help you when you homework. There's a question there. I may attach a video for this one too, but it's coming up. Yeah, very tricky. And let's write this with in blue expenses. Mhm. All right. All right, guys, let's do it together so we can finish, okay? So remember the goal is to maximize minimize the cost, right? This is here, we want the cheapest to enclose. Goal, minimize cost, okay? So we represent our cost with the letter C, right? C. This is gonna be the cost, C. That cost is gonna be equal to what? Look here, $2 per foot, Y feet, 2Y, right? 2Y again here. Here, the cost for X feet, $5 per foot, 5X. But again, here 5X, right? Yeah, this is the total cost. So cost for Y plus 10X. Now I have a constraint. Constraint is that the area is fixed. The area should be fixed, equal to 850, right? 850 square feet, right? 850. But this area is just X times Y, right? Length times width, 850. From here, I can isolate my Y. Y will be equal to 850 over X. And this, I can replace it into my objective function here, right? Right there. So that we deal with one variable for our function, right? Not two, because we don't have the tools to deal with two variables. Yeah. There you go. Now, use your best friend, the Desmos Scientific Calculator, right? Multiply these two guys. 4 times 850.
3,400.
3,400. Thank you, Gonja. 3,400, right? 3,400. Excellent. Over X, right? Plus 10 times X. Now, this should be written this way, right? X raised to minus 1 plus 10X. So that differentiation should be easy, right? So now set derivative equal to 0, solve for X. We do that, the derivative is going to be negative 3400. X raised to negative 1 minus 1 is minus 2 plus 10. That derivative equal to 0. Now, allow me to transpose this to the other side, changing its sign, right? This is this. At this point, we are just doing algebra, right? So this is equal to 3400 over X squared. Multiplying by X squared both sides. I get 10X squared equal 3,400 divided by 10 both sides. This leads to this, right? So X is square root of 340. But what is that? Let's find out. The square root of 340. 18.44. 18.44 rounded to two decimal places, right? 18.44. 18.44. In the end, feel free to attach the units. We're dealing with feet, so feet. Once you found X, then you can find Y. Because Y depends on X this way. 850 divided by X. X is 18.44. So let's do that. So 850 divided by 18.44, 46 point, this will become 46.1, right? 46.1. 46.1 feet. Great. So now X 18.44, 18.44 feet, and Y is equal to 46.1, 46.1. So what should be the answer, guys, in your opinion there? Anybody? Deep. Yeah, good. You got it, Deep. Excellent, excellent. Very good. Good thinking. Yeah, this is saying, right? 18.4 at what price? At $5 per foot, right? This is saying this. And 46.1 at what price? At $2 per foot, right? Yeah, very good. Excellent, excellent. This is it. Yeah, now a comment, guys, here. You may say, Professor, but you have not analyzed the endpoints, Yeah, let me comment on that to finish, right? If you want to deal with the endpoints, look at this part of the cost function, right? If X is close to 0, then what is the cost? Well, this would be infinity, right? Plus 10 times 0, 0, infinity, right? Infinity. Then the cost goes to infinity. That's the endpoint on the left. If X is a huge number, goes to infinity, then the cost function, since this is infinity, a huge number into 3040 is going to be 0, right? It's going to be 0, 10 times infinity, infinity. So C goes to infinity. So the idea is that close to 0 on the XY coordinate, close to 0, the function goes to infinity. For huge values of X, the function also goes to infinity. So given the continuity of this function for values greater than 0, then the minimum should come down here, right? Somewhere. And we found it, right? This minimum value of X is this guy, 18 point, right? It just, again, shows you, right, that the endpoints really, they're not going to change the problem. Try to focus on taking the derivative, setting equal to 0. That's going to be the winner, right, for this type of optimization problem, because the others, they lead to nonsense. Yeah, go ahead.
Can you explain this last part of endpoints again?
Endpoint, yes. Look, let's say you want to find endpoint, right? But think of this. What would be the smallest value of X? Perhaps you would say 0, but if you choose 0, the rectangle will not exist, right? It will not be a rectangle, right? It's nonsense. But even if you get a small value close to 0, this replacing here 0 into this will be a huge number, right? Imagine 0.0001 into this guy. It's going to give you like a trillion or a billion, infinity, and this time 0, 0, right? So see, the cost will go to infinity. It will go up, 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 up. If your X goes to infinity, this will be a huge number. This will be 0 in the limit, and this will be infinity, right? So the cost will go to infinity. So given the continuity is going to infinity, again to infinity continuously, so at some point, it should be the minimum, and that is at the critical point, right? You follow now? Don't worry.
Thank you.
Yeah, very good. It's a good question, but don't worry too much about the endpoints, guys, at this level, because they are not needed. The critical point is the one that will lead to the answer. Okay, guys, we have to end this.